Tonight we are going to ask a question that sounds simple. What would actually happen if you traveled at the speed of light? Not almost light speed, not 99%, the real number, 299,792,458 meters per second. The speed at which light itself moves through the universe. Most people assume the answer is just very fast, that the main problem is the engine, that with enough fuel, enough time, enough engineering, you could build something that crosses that line. You cannot. And the reason has nothing to do with engineering. It is written into the structure of space-time itself. The faster you go, the more energy every additional meter per second costs, not linearly, toward infinity. At exactly light speed, the energy required is infinite. Your mass becomes infinite, and time stops entirely for the traveler. The universe is not withholding this from us. It is telling us something specific about what we are made of. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Sit still for a moment. You are not moving, or so it feels. The room is where you left it. The floor is under you. The walls are in their right place. Nothing is rushing past the window. By every ordinary measure, you are perfectly, completely still. You are not. Right now, at this exact moment, you are moving at roughly 1,600 kilometers per hour because the Earth is rotating. You are also moving at approximately 107,000 kilometers per hour because the Earth is orbiting the Sun. The solar system itself is sweeping through the Milky Way at around 828,000 kilometers per hour, and the Milky Way is streaming through space at somewhere close to 2 million kilometers per hour relative to the oldest light in the universe. You feel none of it. That is not an accident. It is a feature of how space and motion work. There is no universal standstill. There is no privileged position in the universe from which all other motion can be measured as absolute. What you experience as stillness is just the absence of acceleration, the absence of change. The speed itself, whatever it is, does not register in the body. Only the change in speed does. This idea has a name, a reference frame. Your chair is your reference frame right now. Inside that frame, you are stationary. Relative to the center of the galaxy, you are moving at nearly 1 million kilometers per hour. Both statements are correct. Neither one cancels the other out. Motion is always measured against something, and the choice of what you measure it against changes the number without changing the underlying physics. You have been living inside this idea your entire life without knowing its name. You have felt it every time a smooth train made you uncertain which direction it was moving, every time a plane reached cruising altitude and the speed vanished from your body. The speed was still there. The change in speed was gone. And without the change, the body cannot tell. Now here is the part that matters. The universe already knows you are moving at those speeds, and it is already treating your time slightly differently because of it. Right now, satellites in orbit above your head are ticking through time at a slightly different rate than you are. The difference is small. It is measured in microseconds, but at the speed at which GPS signals travel, even a microsecond of timing error compounds. Without corrections for this effect applied constantly and automatically, your GPS would accumulate a position error of roughly 10 kilometers per day. That correction is running right now, every second. Because the relativity is not optional, it is operational. Consider something else. In the upper atmosphere, about 15 to 30 kilometers above the ground, cosmic rays streaming in from deep space collide with air molecules and create unstable particles called muons. A muon is not built to last. Its natural lifespan is roughly 2.2 microseconds before it decays. Even traveling at close to the speed of light, a muon created at 30 kilometers altitude should decay long before it reaches the surface. The math is unambiguous. The distance is too far. The lifetime is too short. And yet muons reach the ground in enormous numbers. Roughly 10,000 of them pass through every square meter of surface every minute. They are passing through you right now. They survive because at the speeds they travel, time slows down for them. From the perspective of the ground, the muon's internal clock is running at a fraction of its normal rate. Its 2.2 microsecond lifetime stretches. The decay that should have ended the muon's existence at altitude is delayed, not by any force, not by any intervention, but simply because time passes differently at different speeds. Time dilation is not a hypothesis waiting for confirmation. It is happening to particles raining down on this planet right now, measurably, consistently, exactly as the equations predict. This is where the question starts. Not with a spacecraft, not with an engine, with your own body in a room that is already moving, in a universe that is already applying these effects at every scale, in every moment, whether or not anyone is paying attention. Now imagine deciding to push that speed deliberately faster, past orbital velocities, past anything a rocket has ever achieved, into the territory where the equations stop being abstractions and start being the physical reality of what the universe is doing to you. What happens then depends entirely on how fast you go, and the answer changes dramatically at every threshold between here and the speed of light. The GPS example is worth sitting with a little longer, because it does two things at once. It confirms that the relativistic effects described in this script are real and operational, and it illustrates the particular strangeness of a universe in which the same physics that governs the behavior of particles in an accelerator also governs the behavior of satellites that millions of people use every day. Before GPS became reliable, navigation depended on maps, compasses, landmarks, and, at sea, celestial observation. All of these methods have uncertainties. A ship's navigator in the age of sail might be off by miles. A land traveller might take the wrong road. The imprecision was acceptable because the alternative was nothing. GPS reduced that uncertainty to meters. It did so using timing signals from a constellation of satellites, each transmitting the precise time from an atomic clock. A receiver on the ground calculates its position by comparing the arrival times of signals from multiple satellites and triangulating. The calculation requires knowing the satellite positions and the signal travel times to extreme precision. At that level of precision, the relativistic corrections are not optional refinements. They are the difference between a functioning system and a broken one. The engineers who designed GPS knew this. They built the corrections in from the start. The satellites were launched with clocks deliberately offset to compensate for the relativistic effects they would experience in orbit. This is not a system that works despite relativity. It is a system that works because its designers understood relativity well enough to account for it in the hardware. The phone in your pocket navigates the world using Einstein's equations. Every time it tells you to turn left in 300 meters, it is confirming that time is not universal, that motion and gravity affect the rate at which clocks run, and that the universe described by special and general relativity is the actual universe you are navigating. The muon example completes the picture the GPS example opens. GPS shows that clocks on satellites run at different rates from clocks on the ground. Muons show the particles moving near the speed of light age more slowly than their stationary counterparts. Together, they establish the reality of time dilation not as a theoretical prediction, but as a practical, measurable, continuously operating feature of the universe as it actually exists. What makes the muon case particularly clean is that it does not require GPS satellites or human engineering. Muons are created naturally by cosmic rays that have been arriving at Earth's atmosphere for as long as the atmosphere has existed. They survive to the surface by the same physics that GPS depends on. The effect is embedded in the natural operation of the universe at every scale, at every speed, in every direction. It is not something special relativity predicts will happen under special conditions. It is something that has been happening continuously throughout the history of the solar system, quietly confirming the equations every second of every day. Before you can understand what happens at the speed of light, you need to understand what it costs to approach it. Speed is not free. This is obvious at everyday scales. Fuel is burned. Energy is consumed. The faster you want to go, the more energy you need. Everyone understands this in principle. What most people have not sat with is the specific way that energy cost scales as speed increases toward light speed, because it does not scale the way intuition suggests. At ordinary speeds, kinetic energy, The energy an object carries by virtue of its motion grows with the square of velocity. Double your speed and you need 4 times the energy. Triple your speed and you need 9 times the energy. This relationship is well established and relatively easy to work with at the speeds of cars and aircraft, and even rockets. But as you approach a significant fraction of the speed of light, this relationship breaks down. The simple formula stops working. A more complete set of equations takes over. And those equations describe something that has no comfortable analogy in everyday experience. The energy required does not merely grow steeply, it grows toward infinity. The approach to light speed is not a hill. It is a wall that gets taller with every step toward it. Think of it this way. Imagine pushing a heavy box across a floor. At first, the box moves slowly and the effort is moderate. You push harder and the box moves faster. But now imagine that as the box approaches some maximum speed, each additional meter per second requires not twice the effort of the previous meter per second, not 10 times but 1,000 times, and then 1,000,000 times, and then more than that. The faster the box moves, the more impossibly expensive each additional unit of speed becomes, not because the box is getting heavier in any ordinary sense, but because the physics of what it means to be a massive object moving through space-time is changing around it. This is not a limitation of the engine. It is a property of mass in a relativistic universe. To make this concrete, accelerating 1 kilogram of material to 10% of the speed of light requires roughly 4.5 times 10 to the power of 14 joules of energy. That is comparable to the energy released by a large thermonuclear weapon. For a single kilogram, to reach 10% of light speed, to accelerate that same kilogram to 99% of light speed requires roughly 6 times 10 to the power of 16 joules, more than 100 times the energy of the first calculation for less than 10 times the additional speed. To reach exactly 100% of light speed, the energy required is not any number. It is infinite. There is no budget large enough. There is no fuel dense enough. There is no power source physics currently allows that could provide infinite energy for any purpose at any scale. Now hold on to that for a moment, because this is only the first wall. It is the engineering wall, the one that would stop any practical mission before it started. But even if you could somehow bypass the energy problem, even if some future physics provided a way to accelerate without conventional thrust, the universe would still have other things to say about what happens to you at high speed. Because as you push toward light speed, the universe does not simply make acceleration more expensive. It starts doing things to time, to distance, to the way light arrives at your eyes, to the very structure of the experience of being a massive object moving through space-time. And those things have nothing to do with the engine. The distinction between the kinetic energy formula at low speeds and the relativistic formula at high speeds is the distinction between two approximations of the same underlying reality. At low speeds, the simpler formula works well enough that the error is negligible. At high speeds, the error accumulates until it becomes the dominant feature of the calculation. A useful way to feel this is to follow what happens to the cost of the last 10% of the journey to C. Going from 0 to 90% of C costs a certain amount of energy. Going from 90 to 99% costs more than 6 times that amount. Going from 99% to 99.9% costs roughly 7 times the previous increment. Each additional decimal 9 costs more than all the previous 9s combined. The sum of the series, if you continued adding 9s forever, would diverge. It does not approach a finite total. It grows without limit because the target is infinite. This is the shape of the wall. It is not a wall with a fixed height that requires a sufficiently large ladder. It is a wall that grows taller faster than any ladder can be built. At every point on the approach to C, the remaining cost is more than the total cost of everything already done. There is no energy density known to physics, no theoretical limit on how concentrated energy can be, that could provide the infinite energy required to reach C, not because the universe lacks energy. The universe contains enormous amounts of energy, but infinite is not a large amount. Infinite is a category that finite quantities, however large, cannot reach. The barrier at C is not high, it is infinite. Those two things are not the same. There is another way to feel the energy cost that does not require calculating joules. Think about fuel. A chemical rocket carries fuel that releases energy through combustion. The energy available is proportional to the mass of the fuel. The more fuel you carry, the more energy you have, but also the more mass you need to accelerate. This creates a circular dependency that limits the achievable speed. The best chemical rockets can achieve perhaps 20 kilometers per second. Nuclear rockets could potentially do better. Ion drives are more efficient. But every conventional propulsion system faces the same underlying constraint. The fuel has mass, the mass limits efficiency, and the efficiency limits what fraction of C can be reached. Even a hypothetical perfect engine, one that converted matter directly to energy with 100% efficiency, the best physically possible fuel, would face the relativistic barrier. Such an engine, consuming its own fuel mass perfectly, could in principle reach significant fractions of C. But the Lorentz factor's divergence near C means that even perfect energy conversion cannot provide infinite energy, because no finite amount of fuel contains infinite energy. The barrier at C is not a barrier that any amount of fuel can overcome. It is the boundary of what finite energy, however efficiently used, can achieve. Suppose against all current physics you had the energy. Suppose the fuel problem was solved, the engineering was ready, and you accelerated your body to 10% of the speed of light, roughly 30,000 kilometers per second, fast enough to cross the entire diameter of Earth in less than half a second. At 10% of light speed, the relativistic effects are present. They are real. They are measurable with precise enough instruments, and they are completely undetectable to any human sense. The Lorentz factor, which is the number that measures how much time and space change at a given speed, sits at approximately 1.005 at 10% of C. For every 100 seconds that pass for the people you left behind, you experience just under 99.5 seconds. Your clock runs about 0.5% slower than theirs. Your body ages at about 0.5% less than theirs. On a one-year trip, you would return roughly 2 days younger than someone who stayed home. 2 days. After a year at 10% of the speed of light, the effect is real. A precise enough clock would confirm it. But your body would not feel it, register it, or survive long enough to notice the difference in any practical sense. What you might notice is something else entirely. At 10% of C, even the near vacuum of interstellar space becomes dangerous. Space is not perfectly empty. It contains stray hydrogen atoms, dust particles, microscopic debris accumulated over billions of years. At ordinary spacecraft speeds, these present no significant hazard. A dust grain at highway speed is a grain of dust. At 10% of light speed, a single hydrogen atom impacts with the energy of a high-velocity bullet. A dust particle, massing perhaps a billionth of a kilogram, carries roughly the kinetic energy of a tank shell. The interstellar medium is not a hazard to be engineered around by adding shielding. At these speeds, adequate shielding against the interstellar medium is itself an unsolved problem in physics and materials science. The faster you go, the more the thin emptiness of space becomes a wall of incoming radiation. But the relativistic effects themselves at 10% are quiet. The stars are in their familiar places. The clock runs almost normally. Time and the traveler are barely separated. That does not last. At 50% of the speed of light, everything changes in a way the body would have to live inside. Not feel physically in the way acceleration presses you into a seat, but live inside in the way that time begins to mean something different in your frame. That it means in the frame of everyone you left behind. There is something important about that number, 30,000 kilometers per second, beyond its sheer magnitude. At 10% of C, you would cross the diameter of Earth in under half a second. You would cover the distance from Earth to the Moon in roughly 13 seconds. In 1 minute, you would travel nearly 2 million kilometers. By any human standard, this is incomprehensibly fast. The fastest spacecraft ever launched by human civilization, the Parker Solar Probe at its closest approach to the Sun, reaches speeds of roughly 700 kilometers per second. 10% of C is 43 times faster than that. The fastest any physical object built by humans has ever moved is less than 0.25% of the speed of light. And yet at 10% of C, the universe is barely responding. The relativistic effects are there, confirmed by precise instruments, but they are producing changes so small that years of travel would accumulate differences measurable in days. The universe has set the dial at a position where the interesting physics has not yet arrived. What has arrived is the danger. At 10% of C, the interstellar medium, the thin gas and dust that fills the space between stars, transforms from an inconvenience into a weapon. The average density of interstellar space is roughly 1 atom per cubic centimeter. That sounds almost like nothing. At rest, passing through this medium is harmless. At 10% of C, each atom encountered carries kinetic energy in the spacecraft's frame equivalent to a high-energy cosmic ray. A dust grain the size of a bacterium, massing on the order of a trillionth of a kilogram, impacts with energy comparable to a rifle bullet. A grain visible to the naked eye would release the energy of a hand grenade on impact. The spacecraft has become not fast enough for the interesting physics and already fast enough for the catastrophic physics of collision. This is a recurring pattern at high speeds. The thresholds where things become interesting in one sense are often thresholds where things become dangerous in another. The universe does not make speed cheap in any direction. At 10% of C, there is also a navigational consideration worth noting. The stars visible ahead of the spacecraft have already shifted slightly from their positions at rest. The aberration is small, less than 3 degrees for stars at the side, but it is non-zero. A spacecraft navigating by stellar positions would need to account for this shift. More practically, communication with any base has already become noticeably delayed. A spacecraft at 10% of C moving away from Earth after 1 hour of travel is approximately 108 million kilometers from its starting point. A signal to Earth takes about 6 minutes one way. A round-trip communication takes 12 minutes. This delay grows every hour. The crew cannot have a real-time conversation with anyone they left behind. They are already in a world of managed delay, where every exchange with home is a message sent into the recent past and a reply received from the recent past. At half the speed of light, the Lorentz factor reaches approximately 1.155. What that number means in practice is this. For every 100 seconds that pass on Earth, you experience roughly 86.6 seconds. Time is not just ticking slower on your clock. Time is passing more slowly in your frame. Your heart beats your thoughts. The decay of cells in your body, the chemical reactions in your brain. Everything that constitutes the experience of being alive is occurring at a slower rate than the corresponding processes in the frame you left behind. In 1 year of travel at 50% of C, you age roughly 10.5 months. The person who stayed on Earth ages a full 12. When you return, the separation is about 6 weeks. 6 weeks younger than someone who was exactly your age when you departed. This is not a clock malfunction. It is not an optical illusion or a philosophical puzzle about what clocks really measure. The difference is physical and permanent. When you return and stand next to the person who stayed, their cells have undergone more divisions. Their telomeres are slightly shorter. Their accumulated biological age is measurably greater. The clocks do not disagree about an abstract thing called time. They disagree about how much of it each of you has lived through. The idea has a name that makes it sound like a riddle. The twin paradox. Take two people who are exactly the same age. Send one away at high speed. When they return, they are no longer the same age. The one who traveled is younger. The paradox seems to emerge when you ask whose frame of reference is correct. If motion is relative, why can you not say the stay-at-home twin moved away at 50% of C relative to the traveler? Surely from the traveler's perspective, the stay-at-home twin was the one doing the traveling. The answer dissolves the paradox. The two situations are not symmetric. The traveler had to accelerate. They had to turn around. They had to decelerate and return. Every one of those changes in velocity was a departure from constant motion. And it is in those moments that the symmetry breaks. The traveler changed reference frames. The stay-at-home twin never did. That asymmetry is real and physically measurable, and it is what produces the age difference. The traveler is genuinely, measurably, biologically younger, not slightly, not negligibly, in a meaningful and irreversible way. At 50% of c, this difference accumulates slowly. A year of travel produces a 6-week gap. But the Lorentz factor does not grow linearly. It does not add equal amounts for equal increases in speed. Near the top of the scale, it accelerates towards something that does not look like ordinary numbers at all. At 90% of c, the separation does not double from 50%. It does not triple. It becomes something the human body would need years to live through. There is a physical reason the twin paradox was named a paradox, even though it resolves cleanly. The confusion arises because of how naturally the principle of relativity can be misapplied. Special relativity says that there is no privileged rest frame. No observer can claim their own frame as the truly stationary one. All motion is relative. From this, it seems to follow that the traveller and the stay-at-home twin have symmetrical situations. Each could claim the other was the one moving. But this symmetry is broken by something the equations are very specific about. Acceleration is not relative. You can feel it. When a spacecraft fires its engines to depart, the occupants are pressed into their seats. When it decelerates at the destination and re-accelerates to return, the occupants are pressed into their seats again. The stay-at-home twin felt none of this. The asymmetry is not a matter of perspective or convention. It is a physically detectable difference between two histories. General relativity provides a complementary way to understand this. From the traveller's frame, the acceleration of the turnaround event can be treated as an equivalent gravitational field. During the turnaround, the traveller experiences something like an intense gravitational field pointing in the direction of their acceleration. In general relativity, clocks deeper in a gravitational field run slower than clocks at higher gravitational potential. During the turnaround, the traveller's effective gravitational field causes the stay-at-home twin's clock to run faster in the traveller's frame, not slower. It is during this short period of acceleration that the bulk of the age difference accumulates. From the traveller's perspective, the two calculations, when using special relativity and the asymmetry of acceleration, when using the gravitational analogy in the traveller's non-inertial frame, agree exactly. The stay-at-home twin is older when they reunite. The amount of the difference depends on the speed and the duration of the trip. The numbers at 50% of c are modest. At higher speeds, the same physics produces separations that span generations. The numbers at 50% of c also reveal something about the difference between the Lorentz factor and the simple Newtonian approximation. In Newtonian mechanics, kinetic energy at half-light speed would be 1/8 of the rest energy, a calculable and finite amount. In special relativity, the kinetic energy at 50% of c is somewhat larger because the Lorentz factor is already above 1. The difference between the two calculations at 50% of c is not enormous, roughly 16%, but is real, and it grows rapidly as speed increases. At 90% of c, the Newtonian calculation is off by a factor of more than 2. At 99%, it is off by a factor of nearly 5. The point at which the simple formula breaks down is not sharp, but the divergence accelerates in exactly the way the Lorentz factor accelerates, because they are describing the same underlying reality from different levels of approximation. At 90% of the speed of light, the Lorentz factor is approximately 2.3. 1 year for the traveller is roughly 2¼ years on Earth. Travel for 5 years at this speed, and you return 11 years after departure. The gap is no longer weeks, it is years. Significant fractions of a life, but 90% of c does something else that 50% did not. It changes what you see. At these speeds, the way light reaches your eyes from different directions is no longer the same as it is at rest. The technical name is relativistic aberration, and it works like this. Imagine walking quickly through rain that is falling perfectly straight down. From your perspective, the rain appears to be coming at you from an angle, tilting toward you from ahead. The rain has not changed direction. Your motion has changed the angle at which it reaches you. Light works the same way. When you are moving at 90% of c toward a region of space, light from stars that are actually off to your sides and even slightly behind you arrives at your eyes as if it were coming from ahead. The stars appear to shift forward. The entire star field, which at rest was distributed across the whole sky, begins to compress toward the direction of travel. At 90% of c, Stars that were originally spread across half the sky have migrated toward the forward hemisphere. Ahead of you, the sky is denser with light than it should be. Behind you, it is darker. The familiar arrangement of constellations has been distorted into something that would be unrecognizable to any astronomer working from Earth. The light from those compressed forward stars also blue shifts. Electromagnetic radiation coming from ahead of you is compressed by your motion into shorter wavelengths. Visible light shifts toward blue and violet. Stars that were white or yellow appear bluer. Some shift toward ultraviolet, invisible to the naked eye. Behind you, the opposite happens. Stars redshift, their light stretched into longer wavelengths, dimmer and eventually invisible to human vision. The universe at 90% of C does not look broken. It looks like the universe seen through a lens that is distorting the whole sky, pulling light from the edges toward a single bright, slightly bluer region directly ahead. At 90% of C, the Lorentz factor is 2.3. The energy required to reach this speed for a human body of 70 kilograms exceeds the energy released by thousands of nuclear weapons. Every kilogram of fuel burned for this acceleration has released more energy than most human nations produce in a year per kilogram consumed. The traveler has not yet approached the territory where the numbers stop being numbers, but they are close. At 99%, the territory changes. The visual experience at 90% of C deserves more attention than the numbers alone provide, because it illustrates something important about what motion at high speed actually does to the physical relationship between an observer and the light reaching them. Ordinarily, when you look at the night sky, light is arriving at your eyes from all directions roughly equally. Stars are distributed across the celestial sphere in a pattern that reflects their actual physical positions. You are, relative to the sky, in effect stationary. Your motion through space is fast by human standards, but slow enough that the light from the stars arrives at your eyes with negligible angular distortion. The sky looks the way it looks. At 90% of C, your velocity is a substantial fraction of the velocity of the light you are receiving. The geometry of how that light reaches you changes fundamentally. Light from stars that are actually off to your sides, that exist at 90 degrees from your direction of travel, arrives at your eyes as if it were coming from approximately 60 degrees ahead. Light from stars that are actually slightly behind you, at angles greater than 90 degrees from your direction of travel, arrives as if it were coming from ahead. The result is that the forward hemisphere of the sky appears to contain not just the stars that are geometrically ahead of you, but the majority of all stars in all directions. The rear hemisphere appears to contain almost nothing. The stars have not moved. The light from them is simply meeting your eyes at angles determined by your velocity relative to the light's source. Combined with the Doppler shift, stars ahead glow bluer and more intensely. Stars behind are dimmer, redder, and eventually invisible. The sky is not merely rearranged. It is transformed into a medium that carries the information of your velocity visibly and dramatically in every direction you look. The blue shift of stars seen ahead at 90% of C also changes their character in ways that go beyond color. Some stars that were in the optical range, visible to the human eye, would be shifted into the ultraviolet. They would become invisible to naked eye observation but detectable to instruments. Some stars in the near-infrared, already barely visible, would be shifted into the optical range and become visible for the first time. The star count in the visible forward hemisphere would change not just because of aberration, but because the observable population would shift. Behind the spacecraft, the reverse is true. Stars in the optical range shift into the infrared and become invisible. The night sky in the rear hemisphere goes dark, not only because the stars have geometrically migrated forward, but because the light they emit in all directions, including backward, has been redshifted below the visible threshold. The spacecraft, at 90% of C, is moving through the same universe as the one it left. But the universe it observes has been transformed by its motion into a configuration that no stationary observer has ever seen, and that would have been very difficult to predict without the mathematics of special relativity. At 99% of the speed of light, the Lorentz factor is approximately 7. 1 year for the traveler is 7 years on Earth. A 10-year trip returns the traveler 70 years after departure. The people who watched the launch are elderly or gone. the world the traveller left has changed through the span of a human lifetime, and the traveller has aged 10 years. This is still not the limit. It is a milestone on the way to something the numbers have difficulty containing. To reach 99% of C, the energy required for a single kilogram of mass is approximately 6 times 10 to the power of 16 joules. That is roughly the energy the sun radiates in 1 millisecond for 1 kilogram. The numbers are beginning to lose their reference points. There is nothing in ordinary human experience to compare them to. Now push from 99% to 99.9%. The Lorentz factor at 99.9% is approximately 22. 1 year for the traveller is 22 years on Earth. The additional energy required to cross from 99% to 99.9% is not a small increment. It is larger than the total energy required to reach 99% in the first place. Each additional decimal 9 costs more than all the decimal 9s before it combined. The Large Hadron Collider at CERN accelerates protons to 99 to 9999991% of the speed of light. A proton has a mass of roughly 1.67 times 10 to the minus 27 kilograms. Negligible. Almost beyond measurement. And yet, accelerating a single proton to that speed requires enough energy to run a household light bulb for several hours. The energy per unit mass is staggering. Now scale that to a human body. A human being mass is roughly 70 kilograms. A proton mass is roughly 1.67 times 10 to the minus 27 kilograms. The human being is approximately 4 times 10 to the 28th times heavier than the proton. The energy required to accelerate a human body to the speeds the LHC reaches with a proton is not computable in any unit that has a meaningful physical reference. This is still not the limit. The proton at those speeds is still below light speed. The Lorentz factor is large but finite. The energy is enormous but finite. There is still a number, even if the number has no comparison. The limit arrives when the speed approaches exactly c, not approximately c, not 99 nines after the decimal. Exactly c. At that point, the Lorentz factor does not reach a very large number. It reaches infinity, and the energy required to produce an infinite Lorentz factor is itself infinite. There is no number large enough. There is no engine powerful enough. The wall is not steep. The wall is vertical. The wall goes up forever. There is something specific that happens to the experience of acceleration as speed approaches c that goes beyond the energy cost. At low speeds, acceleration feels like acceleration. A rocket fires, the occupants feel the push, and speed increases. The relationship between engine thrust and speed gained is approximately linear. More thrust, more speed. Reasonable expectations apply. At relativistic speeds, this relationship has been fundamentally transformed. Not just made more expensive in terms of energy, but made strange in terms of what the traveller experiences and what an external observer measures. From the traveller perspective inside the spacecraft, they can always accelerate. There is no sensation of approaching a limit. If the spacecraft engines provide a constant thrust, the traveller continues to feel that thrust, to experience it as producing acceleration, to feel the increasing force of the engines pushing them forward. In their own frame, their speedometer, if they had one, would show speed increasing. They could, in principle, reach what they measure in their own frame as speeds exceeding c relative to the distant stars. This is not a violation of relativity. The traveller's own measurement of their speed is not the same as what a stationary observer measures. From the stationary observer's frame, the traveller asymptotically approaches c, but never reaches it. From the traveller's frame, they can feel accelerated indefinitely. The two descriptions are consistent because the transformation between the frames, the Lorentz transformation, accounts for exactly this kind of discrepancy. What this means in practice is that an interstellar mission using constant thrust could, from the crew's perspective, travel enormous distances in relatively short experienced time, even though from Earth's perspective they never exceeded c and enormous amounts of time passed during the trip. The constraint is not experiential, it is relational. The traveller cannot exceed relative to any external observer, but their experience of the trip can be as short as their technology allows, by pushing the Lorentz factor as high as the energy budget permits. The The Large Hadron Collider context is worth expanding slightly because it provides the most direct experimental evidence for relativistic mass increase and energy requirements. At CERN, protons are accelerated in a ring 27 kilometers in circumference. To keep them on their circular path, powerful magnetic fields must be applied continuously. As the protons accelerate toward their maximum speed of 99.9999991% of c, the magnetic fields must be increased to compensate for the increasing effective mass of the protons. The relationship between the field strength required and the proton speed follows the Lorentz factor exactly. This is not an incidental feature of the machine. It is the central engineering challenge that every particle accelerator must solve at relativistic energies. The engineers who designed the LHC did not have the option of ignoring relativistic mass increase. If they'd used Newtonian mechanics to calculate the required magnetic fields, the protons would have escaped the ring long before reaching their target speed. The relativistic corrections are not an optional refinement for precision work. They are load-bearing elements of the machine's function. The speed of light is not simply very fast. It is a category boundary. On one side of that boundary, everything that has ever existed in the observable universe, every planet, every star, every spacecraft, every particle measured in any laboratory, every photon of light from a candle flame, moves. All of it, without exception, moves at a speed less than c. On the other side, there is nothing. Nothing with mass has ever existed at exactly c or beyond it, not because the universe is enforcing a traffic law, but because the mathematics describing a massive object at c produces a result that has no physical interpretation. The Lorentz factor contains a term in the denominator, 1 minus the square of the velocity divided by the square of c. At low speeds, this term is close to 1. As speed increases, it decreases. At exactly c, it equals 0. Dividing by 0 does not produce a very large number. It produces something undefined. The equation breaks. The physics breaks. The question of what a massive object at exactly c would experience has no answer, not because the answer is unknown, but because the question contains a contradiction. A massive object at c cannot exist. The two things are mutually exclusive, so what happens concretely if you were somehow at exactly c? The Lorentz factor is infinite. Time dilation factor, infinite. 1 second of traveler time maps to infinite. 1 second of traveler time maps to infinite Earth time. Time has not slowed. Time has stopped. The traveler does not experience the trip slowly. The traveler does not experience the trip at all. There is no duration in which experience can occur. No second passes for the traveler. No heartbeat. No thought. No perception. Between departure and arrival in the traveler's frame, nothing happens. Because nothing can happen in zero time. Mass dilation, infinite. Energy required, infinite. Energy required, infinite. This is not a description of a very extreme physical state. It is a description of a physical impossibility. A massive object at c is not an object pushed to its limits. It is an object that cannot exist at c while remaining a massive object. The category of massive object and the category of object at k do not overlap. The universe does not have a fastest massive object that happens to be moving at c. The universe has two categories of things: things with mass, which move at speeds below c, and things without mass, which cannot move at any speed other than c. Light belongs to the second category, you belong to the first. The proof that a massive object cannot reach t does not rest solely on the Lorentz factor. It is also embedded in the causal structure of spacetime itself. Every event in the universe has a region of spacetime that it can causally influence and a region that it cannot. The boundary between these regions is defined by the speed of light. Information, influence, cause and effect, all of these propagate at most at c. The set of future events that a given event can influence forms a cone shape in the diagram physicists use to represent spacetime, the light cone, and nothing inside the universe moves outside that cone. A massive object moving below c always remains inside its own light cone. Every future position it occupies is causally reachable from every past position it occupied. the world line of a massive object, its path through space-time, is always at an angle less than 45 degrees from the vertical axis of the space-time diagram. It always stays within the cone, and exactly C, the world line would lie exactly on the surface of the light cone. The object would be moving at the boundary between the causally connected region and the region that cannot be causally reached. This boundary is where light itself travels. If an object exceeded C, its world line would lie outside the light cone. It would be in a region of space-time that the physics of causality defines as unreachable from within normal space-time. An object moving faster than C would, depending on the reference frame of the observer, appear to be travelling backward in time. Not metaphorically, literally. In some reference frames, it would arrive at its destination before it departed its origin. This is the causality violation that faster-than-light travel implies. The universe does not permit this, not as a matter of enforcement, but as a matter of logical coherence. A universe where cause could follow effect in some reference frames is a universe without consistent cause and effect at all. The laws of physics as currently understood would be internally inconsistent. The speed of light is the speed of causality. Moving faster than C would be moving faster than the universe's own capacity to maintain its internal consistency. The category distinction between speeds below C and speeds at C is not a distinction of degree. It is a distinction of kind. This is an important clarification because the language of limits can suggest that C is an extreme case of the same continuum that includes lower speeds. It is not. Every speed below C, no matter how close, is physically achievable in principle for a massive object given sufficient energy. The object remains massive. It has a rest frame. It experiences time. There is no physical threshold crossed, no qualitative change in the nature of the object at any speed below C. At C, the situation is categorically different. The object would not be an extreme version of its previous state. It would need to be a different kind of thing. It would need to have zero rest mass. And zero rest mass is not a small rest mass. It is the complete absence of a property that the object, at every speed below C, possessed. You cannot continuously approach zero rest mass by moving fast. You cannot shed rest mass through acceleration. The rest mass of an object is invariant. It does not change with speed. It is what it is, and if it is non-zero, the object cannot be at C. A photon has no rest mass, not negligible mass, not mass so small it barely matters. Zero rest mass. This is not a measurement limitation. It is not that we have tried to weigh photons and found them very light. It is that the property of rest mass, the mass an object has when it is stationary, does not apply to a photon at all. A photon cannot be stationary. There is no frame in the universe from which a photon appears to be at rest. This single fact explains everything the previous chapters have been building toward. The equation that sends the energy requirement to infinity for massive objects contains the rest mass in its structure. As speed increases towards C, the energy required grows proportionally to the rest mass and to the diverging Lorentz factor. For a massive object, this product grows without bound as C is approached. For an object with zero rest mass, the calculation is different. The infinity never appears. The barrier that stops every massive thing from reaching C does not apply to something that has no rest mass to begin with. A photon does not accelerate to C. It does not build up speed from zero. From the moment it is emitted, it moves at exactly k's, because C is the only speed at which something with zero rest mass can exist in a vacuum. A photon has never been slower than C. It cannot be. If it was somehow slowed to below C, the physics would require it to have acquired rest mass, and it would no longer be a photon in the fundamental sense. The speed and the masslessness are not separate properties. They are the same property expressed two ways. Mass-energy equivalence, the relationship described by the equation E equals mc squared, ties mass and energy together in a way that makes the barrier visible. Every kilogram of rest mass represents an enormous quantity of stored energy. Roughly 9 times 10 to the power of 16 joules per kilogram. When you accelerate a massive object, you are not merely adding kinetic energy to something passive. You are working against the resistance that the object's rest energy creates in the structure of space-time. The heavier the object, the stronger the resistance. The faster it already moves, the stronger the resistance to further acceleration. At sea, the resistance becomes infinite, because you would be asking the object to exist in a state that is incompatible with having rest mass at all. A photon does not experience this resistance. It has no rest energy to resist. It slides through the universe at speed the way a shadow slides across a wall, not because it is powerful, but because the constraint that limits everything else does not apply to it. Here is the quiet center of the whole question. You cannot travel at sea because you have mass. The barrier is not external to you. It is not an obstacle placed between you and the speed of light by some rule the universe is enforcing. The barrier is internal. It is the property of being the kind of thing you are: massive, durable, capable of experience. Everything that makes you real in the physical sense is tied to the same property that prevents you from reaching sea. The limitation is not a punishment. It is a description. The deep connection between mass and the experience of time is worth examining from one more angle before moving on. A photon with zero rest mass does not merely travel faster than massive objects. It exists in a fundamentally different relationship with time. For a photon, there is no such thing as elapsed time between emission and absorption. The photon is not old when it arrives. It has not old when it arrives. It has not aged. It has not experienced the trip. In the most precise physical language available, the space-time interval along a photon's path is zero. Not small. Zero. The space-time interval is the quantity that special relativity identifies as invariant, the same for all observers. For a massive object moving below sea, the space-time interval between any two events in the object's history is positive. Time passes. Duration accumulates. For a photon, the interval between emission and absorption is exactly zero, regardless of how far the photon traveled or how long it took in any external frame. This zero interval is what masslessness produces. It is why light can travel at sea. It is why light does not experience the trip. The property of having zero rest mass and the property of traveling at sea and the property of experiencing zero elapsed time are not three separate things. They are the same thing described from three different perspectives. You have a non-zero rest mass. Your space-time interval is positive. You experience duration. Time passes for you. These facts are not independent of each other. They are different expressions of the single physical fact that you are a massive object. The barrier to light speed is not outside you. It is you. The mass that makes you real, the duration that makes you conscious, the temporal existence that gives you a history and a future. These are all tied together by the same physics that prevents you from reaching sea. You cannot have experience in the speed of light. The universe has arranged the two things so that they belong to different categories of object. The relationship between mass and duration is encoded in the mathematics of special relativity in a way that is worth making explicit because it connects the two apparently separate claims of this script that you cannot reach separate claims of this script that you cannot reach psi. And that light does not experience time into one underlying physical statement. In special relativity, there is a quantity called the proper time of an object. The proper time is the time measured by a clock that travels with the object. It is the time the object actually experiences, the time in which its atoms vibrate and its cells divide and its consciousness advances. For a massive object, the proper time between two events is always positive. Duration accumulates. Time passes. For a massless particle, the proper time between emission and absorption is exactly zero. Not approximately zero. Exactly zero. This is what it means for a photon to have no rest frame. The proper time formula, applied to a massless particle moving at sea, produces zero. The particle has no internal clock, no duration, no history between events. This zero proper time is not a coincidence or a curiosity. It is a fundamental consequence of masslessness. The same mathematical structure that sets the rest mass to zero also sets the proper time to zero. You cannot have one without the other. For you, a massive object, the proper time is always positive. You always have a next moment. You always accumulate duration. You are never, in any physically meaningful sense, at the same moment at two different places in space-time. There is always a before and an after. This is what being massive means at the most fundamental level the current equations describe. It means having duration. It means experiencing time. It means being a being that exists in sequence rather than all at once. You cannot reach because you have duration. And you have duration because you have mass. The two things are one thing. Two people, the same age, stand at a spaceport. One boards a spacecraft. One space. The traveller departs at 90% of the speed of light toward a star 4¼ light years away. From Earth's perspective, the trip takes just under 5 years each way. The traveller returns roughly 10 years after departure. The stay at home has aged 10 years. The traveller has aged roughly 4 years and 4 months. They stand next to each other. The gap between them is not philosophical. It is not a matter of perception or definition. It is approximately 5½ years of biological age. The traveller is younger, not metaphorically, not as a trick of the clock, younger in every physical, chemical, cellular sense of the word. This is the twin paradox, and it is not a paradox. It seems paradoxical because the principle of relativity says that motion is relative. If the traveller is moving at 90% of c relative to Earth, one could equally say Earth is moving at 90% of c relative to the traveller. From the traveller's perspective, the stay-at-home twin is the one flying away and returning. Shouldn't the stay-at-home then be the younger one? No. And the reason is the asymmetry. The traveller accelerated. They left Earth by accelerating to 90% of c. They decelerated to stop at the destination star. They accelerated again to return. They decelerated again to land on Earth. Every one of these events, every change in velocity, every departure from constant straight-line motion, is an event that occurred for the traveller and not for the stay-at-home twin. Acceleration is not relative. You can feel acceleration. When a car turns a corner, the passenger is pressed against the seat. When a rocket fires, the astronaut is pressed into the couch. There is no ambiguity about who is accelerating and who is not. The traveller felt every boost and every braking burn. The stay-at-home felt none of it. That physical difference between the two histories, the traveller's history of acceleration and the stay-at-home's history of steady inertia, is what breaks the symmetry. It is what makes the two clocks genuinely disagree, rather than merely appear to disagree from different vantage points. The disagreement is real. It accumulates throughout the trip and is permanent when they reunite. The traveller cannot get those years back. The stay-at-home cannot give them up. Time did not slow for the traveller in a way they noticed. From inside the spacecraft, a day felt like a day. A month felt like a month. But when the two frames are compared, the traveller lived through fewer of them. The universe does not make mistakes about this. Every atomic clock on every aircraft ever flown has confirmed the effect at the small scales that aircraft speeds allow. Every particle accelerator that has ever measured the decay rate of fast-moving particles has confirmed it at larger scales. The twin paradox resolves not into impossibility, but into a clean, experimentally verified, mathematically precise description of something the universe does routinely at every speed, in every direction, all the time. Time is not universal. It is local. Each massive object carries its own clock, and the rate at which that clock runs depends on how the object moves. What the twin paradox reveals beyond its mathematical resolution is something about the nature of shared reality. When the two twins are together at the spaceport at the beginning, they share a moment. The same now. The same present. They can look at each other and agree on everything about the current state of the universe as they both experience it. Their clocks agree. Their ages agree. Their histories have unfolded at the same rate in the same place. When the traveller returns, this shared reality has been permanently disrupted. The traveller and the stay-at-home have not merely experienced different amounts of time. They have, in a deep physical sense, lived through different amounts of the universe's history. The traveller experienced fewer heartbeats, fewer cell divisions, fewer accumulations of everything that constitutes biological aging. The stay-at-home experienced more of all of those things. The moment of reunion is not a return to shared reality. It is the meeting of two people who have travelled through different amounts of the same universe. They are not equivalent observers who happen to have different ages due to a quirk of perspective. They have genuinely aged differently. The difference is as real as any other physical measurement. This has a consequence that is rarely discussed in popular accounts of the twin paradox. The traveller, upon returning, is not merely younger, they are, in a precise physical sense, from an earlier era. The world they return to has undergone years of change that they did not witness. If they travelled at high enough speed for long enough, the change could be civilizational. The traveller would return to a world that had moved on without them, aged past them, developed in directions they had no part of. The speed of light does not merely limit how fast you can go. Through time dilation, it shapes what going fast does to your relationship with everyone you left behind, not just the separation of distance. The separation of time. The twin paradox also reveals something important about what now means at cosmological scales. On Earth, at ordinary speeds, the concept of a shared present moment is unproblematic. You and the person across the room agree on what time it is. Your clocks differ by fractions of microseconds at most. For practical purposes, you share a now. Over large distances and high speeds, this breaks down. Two observers moving at different velocities and separated by large distances do not agree on which events are simultaneous. An event that is simultaneous with another event in one frame is not simultaneous in another. Simultaneous in another. Simultaneity is frame-dependent. The present moment is not a universal slice through the universe, but a local, frame-specific construction. This means that the question what is happening on Earth right now, while travelling at 90% of c, is not merely unanswerable due to the communication delay. It is a question without a single correct answer. The traveller's frame and Earth's frame slice through space-time differently. The set of events that constitute now for the traveller does not match the set that constitute now for people on Earth. The two present moments are tilted relative to each other in space-time, and this tilt grows with distance and speed. Time dilation changes the traveller's experience of duration. Length contraction changes their experience of distance. At 99% of the speed of light, the Lorentz factor is approximately 7. This means not only that time passes 7 times more slowly for the traveller than for a stationary observer, it also means that the traveller experiences distances as approximately 7 times shorter than a stationary observer would measure them. Alpha Centauri, the nearest star system, is roughly 4.25 light-years from Earth. At rest, from either end, this distance measures 4.25 light-years, but for a traveller moving at 99% of c toward Alpha Centauri, the distance to the destination is not 4.25 light-years, it is approximately 0.6 light-years. The space between the traveller and the destination has physically contracted in the traveller's frame by the Lorentz factor. This is not an illusion. It is not a perceptual trick caused by the traveller moving so quickly that they arrive sooner. It is a real, frame-dependent property of space. The traveller is not merely getting to the destination more quickly. In the traveller's frame, the destination is genuinely closer. Think about what this means in practice. A traveller at 99% of c heading for Alpha Centauri would complete the trip in approximately 0.6 years of their own time. Not 4.25 years, not even 4.25 years compressed by time dilation. 0.6 years, less than 8 months. Alpha Centauri is reachable within a human lifespan at 99% of c in the traveller's experience time. From Earth's frame, the trip still took roughly 4.3 years. The distance Earth measured was still 4.25 light-years. The traveller did not break any speed limit. They did not arrive before the light from their departure. No causality was violated. But the traveller experienced the trip as far shorter, because in their frame, the trip was far shorter. Length contraction and time dilation are not separate effects. They are two aspects of the same underlying geometry of space-time. When you move through space, you move through time at a different rate, and the space you move through is also different from the space a stationary observer measures. These two changes are precisely related by the same Lorentz factor. They are the same thing expressed in 2 dimensions. This is the opening the speed limit leaves, not a way through the wall, but a tunnel that runs through the wall from the traveller's side, compressing the distance while leaving the speed limit intact. The traveller cannot exceed c, but they can cover distances that seem from Earth to require years of travel. In their own experienced time, there is a fraction of those years. The stars are not unreachable. They are reachable at a cost, not of speed, of separation. Length contraction has a practical implication that is worth following through carefully because it changes the arithmetic of interstellar travel in a specific way. From Earth, the distance to Alpha Centauri is 4.25 light-years. A spacecraft traveling at 99% of c would cover that distance in approximately 4.3 years from Earth's frame. The crew aboard would experience that trip as lasting approximately 7 months due to time dilation. Their clocks tick 7 times slower than Earth clocks at 99% of c. But from the crew's perspective, it is not that the trip took only 7 months despite the distance being 4.25 light-years. From the crew's perspective, the distance was not 4.25 light-years. It was approximately 0.6 light-years. The distance itself is contracted by the Lorentz factor. The crew is not experiencing a compressed version of a 4 light-year trip. They are genuinely traveling through what, in their frame, is a shorter distance. Both frames are correct. Earth measures 4.25 light-years and 4.3 years. The crew measures 0.6 light-years and 7 months. Neither measurement is more real than the other. They are equally valid descriptions of the same physical reality expressed from different frames. This relationship between length contraction and time dilation is not coincidental. The two effects are locked together by the Lorentz factor. Whatever factor time slows by, space contracts by the same factor. They are two manifestations of the same underlying transformation of space-time coordinates between reference frames. The practical consequence is that interstellar distances are not fixed obstacles, they are frame-dependent measurements. A traveller at sufficiently high speed experiences the universe as a more compressed place. The stars, while no closer to each other from any external perspective, are closer to each other from the perspective of a traveller moving between them at a large fraction of c. The speed limit does not prevent reaching distant destinations within a human lifetime. It prevents reaching them without leaving the rest of humanity behind in time. The question of what length contraction means physically is one that students of special relativity frequently find confusing. The key is to be precise about what is being contracted. Length contraction is a statement about measurements. When an observer in frame A measures the length of an object moving relative to them in frame B, they obtain a different value than an observer at rest relative to the object in frame B. Both measurements are performed correctly. Both are real. Neither is an illusion. They simply refer to different physical quantities. A rod at rest in frame B has a specific proper length. Observers in frame B agree on this length. Observers in frame A with the rod moving past them measure a shorter length because the front and back of the rod do not occupy the same space at the same time in frame A as they do in frame B. The simultaneity difference between the frames is what produces the length difference. This is why length contraction and time dilation are inextricably linked. They are both consequences of the same underlying fact that the definition of the same time differs between frames. Resolve the simultaneity question and you get both the time dilation and the length contraction. They are not two separate relativistic effects. They are one effect seen from two different perspectives. At speeds approaching light, the universe outside the spacecraft window does not look fast. It looks wrong. At 10% of c, the star field is almost familiar. The stars are in their expected places. The constellations hold their shapes. A trained astronomer looking out the window would recognize the sky, with perhaps a few subtle shifts that precise measurements would confirm but that the eye would not catch. At 50% of c, the shifts are becoming visible. Stars toward the direction of travel appear slightly brightened. Stars behind the ship appear slightly dimmer. The distribution is no longer perfectly even. At 90% of c, the sky has rearranged itself in a way no ordinary experience prepares you for. Relativistic aberration, the same effect that makes rain seem to tilt toward a moving car, has compressed the starfield toward the forward direction of travel. Stars that were distributed across the entire sky have migrated into the forward hemisphere, The stars ahead are packed together and blue shifted, their light arriving at shorter, higher energy wavelengths, making them appear bluer and brighter than they should be. Stars that were visible behind the ship have shifted toward the edges of the visible sky. Some have moved into infrared and become invisible. The forward hemisphere glows. The rear hemisphere dims. At 99% of C, the effect is concentrated further. The compressed circle of blue-shifted stars ahead now covers roughly the forward 30 degrees of the visual field. Half the stars in the sky are packed into that circle. The light arriving from ahead has been blue-shifted into the violet end of the spectrum. Some wavelengths have shifted entirely into ultraviolet, invisible without instruments. At 99.9% of C, the circle has shrunk to perhaps 8 or 10 degrees. A bright, intensely blue, almost violently compressed disk of stellar light, sitting dead ahead, while the rest of the universe recedes into a deepening dark. The ship is not flying toward the stars. The stars are being pulled toward the ship by the geometry of its motion. At speeds approaching c still further, the forward disk would continue to compress. The wavelength of the arriving light would continue to shift toward higher and higher energies. The blue would become ultraviolet. The ultraviolet would become X-ray. The X-ray would become gamma radiation. The entire light of the observable universe, every photon from every star in every galaxy, would be compressed and blue-shifted into a single point of concentrated lethal radiation directly ahead. The universe at the approach to C is not a place the human body can survive without protection of a kind that does not exist. It is also a view unlike anything seen from a planet's surface, or even from low Earth orbit. It is the universe reorganized by velocity into a geometry that has no counterpart in ordinary human experience. It is what the universe looks like when you push toward the boundary of what motion means. The transformation of the visual sky at near-light speed raises a question that is worth addressing directly. What would the traveler actually do with this information? The answer is that at the speeds where aberration becomes extreme, the traveler requires instruments rather than eyes. The human visual system is calibrated for ordinary environmental conditions. It evolved to process light arriving in roughly its natural wavelength distribution, from directions that correspond to the actual positions of objects. At 99% of C, neither of these conditions holds. Stars that are actually to the sides and behind the traveler appear ahead and blue-shifted. Navigation by eye would be meaningless. The apparent positions of stars bear no simple relationship to their actual positions. Any real spacecraft traveling at these speeds would navigate by computation, using the known physics of aberration and Doppler shift to back-calculate the actual positions of objects from the distorted apparent positions. The navigation problem is solvable, but it requires treating the sky as a transformed coordinate system rather than a direct view. There is also the radiation problem. The blue shift of incoming light is not merely a visual phenomenon. When visible light is shifted toward higher frequencies, it becomes ultraviolet. When ultraviolet light is shifted further, it becomes X-ray radiation. At sufficient speeds, even the microwave background radiation of the universe, the faint glow left over from the Big Bang, would be blue-shifted into visible light and eventually into harmful radiation. At speeds very close to C, the forward hemisphere would flood the spacecraft with energies that would be lethal to biological organisms and damaging to electronics without extreme shielding. The visual transformation of the sky is not just a curiosity. It is a symptom of the broader physical transformation the universe undergoes in the traveler's frame. A transformation that makes survival at near-light speed a substantial engineering challenge even before the energy problem is considered. The radiation environment at near-light speed has one more aspect worth noting. Even without the blue shift of starlight, the interstellar medium itself becomes a radiation hazard. The interstellar medium contains magnetic fields, and charged particles moving through magnetic fields experience a force perpendicular to their motion. At the speeds we are discussing, the energy of cosmic ray protons encountered in the interstellar medium, boosted by the spacecraft's approach velocity, would penetrate any currently conceivable shielding material. The secondary particles produced by cosmic ray interactions with the shielding would themselves be energetic enough to be biologically damaging. This is not a problem unique to near light speed, but it scales severely with velocity. At 1% of c, cosmic ray shielding is a manageable engineering problem. At 99% of c, it is an unsolved physics problem. The energy scales involved in near light speed encounters with the interstellar medium are at the frontier of what particle physics describes, and the material science that would be required to shield against them does not exist. The romantic image of near light speed travel, a spacecraft gliding silently through a compressed star field, amidst the physical reality that the spacecraft would be traveling through what is at those speeds, a hard radiation environment with no currently known adequate protection. The energy problem has been present since the second chapter, but there is a reason to return to it now, after the Lorentz factor, after the twin paradox, after the visual distortions at high speed. Because those phenomena give the energy problem a different texture, they make it clear that the wall is not merely steep. It is the same wall in every direction. The faster you go, the more the Lorentz factor diverges. The more the energy required diverges, the more extreme the relativistic effects become. All of them pointing at the same limit, all of them describing the same boundary in different physical languages. Mass-energy equivalence, E equals mc squared, is the equation that makes this wall legible. What the equation says in physical terms is that mass and energy are the same thing in different forms. A kilogram of matter sitting completely still, doing nothing, interacting with nothing, contains an amount of energy equal to its mass times the speed of light squared. 1 kilogram contains roughly 9 times 10 to the power of 16 joules of rest energy. That is the energy of a large thermonuclear weapon stored in 1 kilogram of any ordinary matter before you have added any kinetic energy at all. When you accelerate that kilogram, you are adding kinetic energy on top of this enormous rest energy. At everyday speeds, the kinetic energy added is negligible compared to the rest energy. At 10% of c, the kinetic energy is still relatively small compared to the rest energy, but as you push towards c, the kinetic energy grows without bound, and the total energy of the object, rest energy plus kinetic energy, approaches infinity along with the Lorentz factor. This is why the wall is infinite, not because the universe has decided that c is the speed limit and is enforcing it with increasing force, but because the energy content of a massive object moving at exactly c would have to be infinite, and infinite energy does not exist in finite amounts anywhere in the universe. The equation E equals mc squared is often described as one of the most elegant in all of physics. It is also one of the most constraining. It ties you to the rest energy of your own mass. It tells you that the atoms you are made of already contain an incomprehensible amount of energy just by existing, and it tells you that trying to push those atoms to c requires adding infinitely more energy on top of that existing store. You are not being blocked by an external force. You are being contained by what you are, now. Every few years a proposal appears that claims to find a door in this wall, a loophole, a topology of space-time that allows, if not traveling through space faster than light, then some other arrangement that produces the same practical effect. These proposals are worth taking seriously. Some of them come from serious physicists, and the honest assessment of each of them is worth understanding. The most well-known is the Alcubierre drive. In 1994, physicist Miguel Alcubierre published a paper demonstrating that Einstein's field equations, which describe how mass and energy walk space-time, permitted a solution in which a region of space could be contracted ahead of a spacecraft and expanded behind it. The spacecraft itself would sit inside a bubble of flat space-time, experiencing no acceleration, while the bubble itself moved through space. The spacecraft would not be traveling through space faster than light. Space itself would be moving around it. This is mathematically valid. The solution exists within general relativity. It does not violate the speed limit for motion through space because the ship is not moving through space in the conventional sense. There is one problem: to create and maintain the warp bubble. The solution requires exotic matter, a hypothetical form of matter with negative energy density. Negative energy density means that the matter contains less energy than empty space, which requires negative mass, a concept with no confirmed physical existence. The Casimir effect demonstrates that quantum mechanics can produce regions with slightly negative energy density between closely spaced conductive plates, but the amounts are fantastically small, confined to microscopic gaps, and cannot be accumulated, directed, or scaled up to any useful quantity. The original Alcubierre solution required exotic matter equivalent in mass energy to the planet Jupiter, though later refinements reduced this estimate substantially. But the requirement for negative energy density in any quantity that functions as required has not been removed. As of current physics, exotic matter in the form that Alcubierre drive requires has never been observed to exist in any usable amount. The drive remains a mathematical curiosity that describes a valid spacetime geometry without describing a physically buildable object. Traversable wormholes face the same problem. They require exotic matter to remain open. Without it, a wormhole would collapse before anything could pass through. Quantum tunneling allows particles to cross barriers. They classically could not. But it does not allow information to travel faster than light in any way that preserves causality or enables communication. Every door in the wall leads to the same room, the room where the physics requires something the universe has not provided. The Alcubierre drive represents one of the more interesting intersections of legitimate physics and speculative engineering. It is worth being precise about exactly what status it holds. The Alcubierre metric is a valid solution to the Einstein field equations. This means that a space-time with the geometry Alcubierre described is mathematically self-consistent within general relativity. It does not violate the equations. A universe where this geometry existed would obey the laws of physics as currently formulated, but mathematical consistency is not the same as physical realizability. General relativity permits many space-time geometries that cannot exist in practice because they require energy conditions that the known matter and energy of the universe do not satisfy. The exotic matter required by the Alcubierre metric, matter with negative energy density, violates what physicists call the weak energy condition. No known form of matter or energy has negative energy density in the required amounts. The Casimir effect, as mentioned earlier, produces tiny regions of negative energy density between closely spaced conducting plates. This is a real quantum mechanical effect, but the energy densities involved are fantastically small, and the geometry is constrained to the tiny gap between the plates. Scaling this effect to produce the warp bubble geometry Alcubierre described would require negative energy in quantities that current physics cannot identify any source for. Later work by Harold White at NASA reduced the theoretical energy requirements substantially to the equivalent of a large spacecraft mass rather than a planetary mass. This is progress in the mathematics, but the requirement for negative energy density in any significant quantity remains, and negative energy density in those quantities has no confirmed source in physics. The honest statement about the Alcubierre drive is that it describes a geometry that would work if exotic matter exists in usable quantities, and that no evidence currently exists that it does. It is a genuine contribution to theoretical physics. It is not a blueprint for an engine. The speed of light is 299,792,458 meters per second exactly. Not approximately, exactly. Since 1983, the meter has been defined in terms of the speed of light. 1 meter is the distance light travels in a vacuum in 1/299 millionth of a second. The speed of light is not a measurement that could in principle come out differently with better instruments. It is a definition. The universe has a speed built into its structure, and the human system of measurement has been re-anchored to that speed. Why is it this number and not some other number? That question has two answers, and both are worth sitting with. The first answer is that the number depends on the units. In meters per second, c is approximately 300 million. In feet per second, it is approximately 984 million. In light years per year, it is exactly 1. The magnitude of the number is not fundamental. The number itself is a product of the human choice of units. What is fundamental is the constant itself, the fact that this speed exists, that it is invariant, that every observer in every frame measures the same value for c, regardless of their own velocity. The second answer is deeper and stranger. When James Clerk Maxwell unified electricity and magnetism in the 1860s, his equations described how electric and magnetic fields propagate through space. Those equations predicted that electromagnetic waves travel at a specific speed. When Maxwell calculated that speed from the fundamental constants of electromagnetism, The number he obtained matched the measured speed of light. Light was not a separate phenomenon that happened to travel fast. Light was an electromagnetic wave, and the speed at which electromagnetic waves propagate is not a property of light in particular. It is a property of the electromagnetic field itself, which is to say, a property of space-time. The speed of light is the speed at which changes in the electromagnetic field propagate through the vacuum. It is also the speed at which changes in the gravitational field propagate, as confirmed by the detection of gravitational waves. It is the speed at which any massless field propagates through the vacuum. It is the speed at which cause and effect propagate through space-time itself. When something happens, the effect of that event spreads outward at c. No effect reaches any point before c allows it to. This is not a limitation on how fast effects can travel. This is what the universe means by cause and effect. C is the clock rate of causality. It is the speed at which the universe processes information about itself. You cannot exceed it, not because you lack a powerful enough engine. You cannot exceed it because you are inside the universe, made of the universe, operating under the same laws that define what cause and effect mean. To exceed C would be to receive the effect of an event before the event occurred. The universe does not permit this, not as a rule but as a logical structure. Effect before cause is not merely unlikely. It is not merely prohibited. It is incoherent. The speed of light is the speed at which the universe thinks. The invariance of C is not merely a statement about light. It is a statement about space-time itself. Einstein's great insight in developing special relativity was not that light travels at a constant speed. Though Michelson and Morley had established this experimentally, his insight was that this constancy, if taken seriously, required rethinking the relationship between space and time. If every observer in every frame measures the same speed for light, then the intuitive Newtonian picture, in which time is absolute and the same for everyone, must be wrong. Time must be rolling. Time must be relative too. From this single observation, the constancy of C, almost everything else in special relativity follows. The Lorentz transformation, time dilation, length contraction, mass-energy equivalence, the impossibility of exceeding C, all of these emerge as necessary consequences of taking seriously the experimental fact that light travels at the same speed in every reference frame. The reason this is true turns out to be deep. In special relativity, space and time are not separate things. They are aspects of a single four-dimensional manifold called space-time. Events in space-time have a location in 3 dimensions of space and 1 dimension of time. The separation between events is not purely spatial or purely temporal. It is a combination, and the invariant quantity, the quantity that all observers agree on regardless of their velocity, is not the spatial distance and not the time interval, but a combination of both. The space-time interval. The speed of light is invariant because c is the conversion factor between space and time in this unified space-time. It tells you how many meters of space correspond to 1 second of time in the geometry of the universe. Changing the value of c would be changing the geometry itself. It would be changing what it means for 2 events to be separated in space-time. The value of c is not arbitrary. It is the fundamental constant that relates the 2 aspects of space-time to each other. There is a way in which the constancy of c represents a kind of democracy in physics. In Newtonian mechanics, the speed of light was just a speed. It was fast, but in principle, an object moving fast enough could catch up to a light beam. The speed of light was not special in any structural sense. It was simply the speed at which electromagnetic radiation happened to propagate, derivable from the properties of the electromagnetic medium. In special relativity, c becomes the conversion factor between space and time, the quantity that makes the space-time interval invariant, the speed that all massless entities travel at in vacuum. It is no longer just the speed of light. It is the speed at which the geometry of space-time is defined. This means that c is not fast relative to some absolute scale. It is the scale. Every velocity is measured as a fraction of c. Every time interval and space interval are related to each other through c. The universe has exactly one fundamental velocity, and it is c, and everything else is expressed relative to it. The fact that you cannot travel at c is therefore not a fact about being slow. It is a fact about being embedded in the geometry that c defines. You are inside the universe made of the same fields and particles that C describes, operating under the same laws. You cannot exceed the speed at which the universe processes its own geometry for the same reason you cannot stand outside the universe and observe it from a detached perspective. There is no outside. There is only inside. And inside, C is the fundamental scale. The stars are separated by distances that light itself takes years to cross. Alpha Centauri, 4.25 light-years. The center of the Milky Way, 26,000 light-years. The Andromeda Galaxy, 2.5 million light-years. At the speed of light, these are trip durations measured in years, centuries, millions of years, at the speed anything with mass can reach, which is always somewhat less than c. They are longer still. This looks like an insurmountable barrier to reaching the stars. But time dilation changes what that means. The barrier to crossing interstellar distances is not that the distances exceed what a human lifetime allows. The barrier is subtler. It is the asymmetry that high-speed travel creates between the traveler and everything they leave behind. At 99% of c, the Lorentz factor is roughly 7. A trip to Alpha Centauri takes approximately 4.3 years from Earth's perspective, and approximately 7 months from the traveler's perspective. The traveler ages 7 months. Earth ages 4 years. The traveler returns roughly 7.5 years after departure and has aged 14 months in total. The separation between their biological age and the age of someone who stayed is approximately 6 years. This is survivable. It is strange and permanent, but it is not catastrophic. The traveler went to the nearest star and came back younger than their sibling by 6 years. Push further. At 99.9% of c, the Lorentz factor is roughly 22. A trip to a star 22 light-years away would take 22 years from Earth's frame and 1 year from the traveler's frame. And 1 year from the traveler's frame. The traveler ages 1 year. Earth ages 22. And further. At 99.9999% of c, the Lorentz factor approaches thousands. A traveler could reach the Andromeda Galaxy, 2.5 million light-years away, in something like 1,000 years of their own experienced time. 2.5 million years would pass on Earth during that trip. The stars are reachable. But only by leaving. Only by accepting that the world the traveler returns to, if they return at all, will be unrecognizably transformed. The people who watched the launch will be dead. Their children will be dead. Their children's children's children will be dead, perhaps many times over. The speed limit does not make the stars unreachable. It makes them reachable only at the cost of connection. The traveler can go. They cannot go and come back to anything familiar. The universe will not hold still while they travel. The universe does not offer that deal. This is the practical reality of what the title question reveals. You could in principle travel at near light speed. You cannot travel at exactly c. But even the near approach is not a solution to reaching the stars and returning home. It is a solution to reaching the stars while sacrificing home entirely. The asymmetry the speed limit creates between traveler and home is not merely a consequence of time dilation, it is a consequence of the one-way nature of the separation. When the traveler departs at high speed, their clock begins to diverge from Earth clocks. But the divergence is private. The traveler cannot send information home at a rate that compensates for the time difference. Any message they transmit toward Earth travels at c, no faster. From Earth, messages from the traveler arrive red-shifted and less frequently than the traveler is sending them. From the traveler's frame, messages from Earth arrive blue-shifted and more frequently. Neither party experiences the divergence in real time in a way that allows correction. The divergence accumulates silently, privately, in the physics of the respective frames and is only revealed at reunion. This means there is no way for the traveler to know, in real time, what is happening on Earth during their transit. They can calculate it. They know the physics. They can work out that if they are traveling at 99% of c, and have been doing so for 1 year of their time, approximately 7 years have passed on Earth, they can work out that anyone who was elderly when they left is likely gone. They can work out the approximate state of the world based on the speed and duration of travel. But knowing is not the same as experiencing. The traveler cannot participate in the 7 years passing on Earth. They cannot communicate in real time. They cannot intervene. They are, for the duration of the trip, cut off from the temporal community of Earth, not by distance alone, but by the specific way that high-speed travel interacts with the structure of space-time. This is the cost that the speed limit extracts for any approach to it, not merely the energy cost of acceleration, the relational cost of time. Every step towards C increases the divergence between the traveler's experience time and Earth's experience time. The universe does not make this compensation elsewhere. There is no technology that gets the years back. Time dilation also means that the universe offers a strange gift to the traveler willing to accept permanent separation from everything they know. The gift is access to timescales that would otherwise be impossible. A traveler at sufficient speed could, in their own experienced time, witness the far future of the cosmos. Not quickly, not without cost, but genuinely. A traveler accelerating at 1 g, the same gravitational acceleration felt on Earth's surface, which is the maximum comfortable constant acceleration for a human body over extended periods, would reach 99% of C after roughly a year of travel. After 2 years of proper time, they would be moving at nearly 99.9% of C. After 3 years, approaching 99.99%. At this point, the Lorentz factor has grown to several hundred. For every year the traveler experiences, several hundred years pass in the outside universe. A traveler undergoing continuous 1 g acceleration and deceleration could reach the center of the Milky Way, 26,000 light-years away, in approximately 20 years of their own time. They would arrive to find that 26,000 years had passed on Earth. They could reach the Andromeda Galaxy in about 28 years of their own time. 2.5 million years would have passed back home. These trips are physically possible. No law of physics prevents them. The energy requirements are staggering, far beyond anything humanity could currently provide for a manned spacecraft. But there is no theoretical limit that says they are impossible in principle. The way C as an exact limit is impossible in principle. The universe is not locked in its current state from the traveler's perspective. Given sufficient speed and the willingness to lose all connection to the era of departure, a human being could, in their biological lifetime, move through millions of years of the universe's history. Close your eyes for a moment and consider what a photon does. A photon is emitted from the surface of the Sun. In the moment of its emission, it is moving at exactly C, not accelerating towards C, not building up from a standing start, moving at C from the first instant of its existence. It crosses the 8 light minutes between the Sun and Earth in 8 minutes. It enters your eye, is absorbed by a photoreceptor, and triggers a chemical reaction that becomes a signal in your nervous system, and you see. From your perspective, the photon left the Sun 8 minutes ago and traveled across space to reach you. From the photon's perspective, if it had one, it did not travel at all. It was emitted and absorbed in the same instant, not the same very short instant. The same zero-duration instant. Between emission and absorption from the photon's frame, no time passed. The Sun and your eye occupied the same moment. There was no trip. There was no duration. There was no experience of crossing space. The photon has no perspective in any real sense because having a perspective requires a rest frame, and a photon has no rest frame. But the mathematics is clear. A massless particle moving at C does not experience time. It does not move through time the way you do. It is, in the deepest physical sense, outside of time entirely. You are not outside of time. You are inside it, completely, unavoidably. Every second of your existence is a second that passes at the rate your reference frame allows. Your cells divide. Your atoms decay. Your consciousness advances. You are a being of duration. Everything that makes you a living thing, a thinking thing, a feeling thing, is built from processes that require time to unfold. The photon has none of this. Zero rest mass, zero duration, no experience, no age, no history. It is emitted and absorbed and nothing happens in between. Because from its non-existent perspective, there is no between. You are the opposite of a photon in every physical sense. You have mass, You have duration, you have experience, you have history. All of those properties are tied together in the physics of what you are. The same property that gives you mass also gives you duration. The same property that gives you duration also prevents you from moving at sea. You cannot have the experience and the speed. The universe does not offer both. This is not a philosophical observation. It is a physical constraint. The structure of spacetime connects mass, duration, and maximum speed in a way that cannot be separated. A thing that moves at sea must have zero rest mass. A thing with zero rest mass does not experience time. A thing that does not experience time is not alive in any sense the word applies to. You cannot travel at the speed of light because you are alive. The speed limit is not a rule applied to you from outside. It is a consequence of being the kind of thing that can ask the question. There is a version of the question posed in this title that asks not about the traveller, but about the observation. What would it look like, from Earth, to watch someone accelerate toward the speed of light? The answer is that you would not watch them accelerate. You would watch them slow down. As the traveller moves away from Earth at increasing speed, the light they emit takes longer and longer to reach Earth. From Earth's perspective, the traveller's clock appears to run slow, not merely by the Lorentz factor, but by an additional factor from the Doppler shift. The traveller's transmissions arrive stretched and slow. Their voice becomes lower. Their image appears to move in slow motion. As the traveller approaches sea, this effect becomes extreme. The traveller who left 10 years ago from the traveller's frame appears on Earth to still be transmitting from moments after departure. Their light is arriving years late. From Earth, the traveller appears frozen at a point shortly after leaving, transmitting in ultra-slow motion, red-shifted into oblivion. The traveller, looking back at Earth, would see the opposite effect. Earth's transmissions would arrive blue-shifted and fast. Years of Earth's history would compress into the traveller's experienced months. Earth would appear to be living in fast-forward. Neither of these is an illusion. Both are direct consequences of the finite speed of light and the Doppler effect applied to spacetime itself. The traveller who approaches sea does not become invisible or supernatural. They become unreachable in a specific and calculable way. Their light takes so long to arrive that their current state is always in the deep past from Earth's perspective. They are present in the universe, moving through it, but separated from any shared present moment with anyone they left behind. The speed limit severs not just the physical connection, but the temporal one. The closing observation about photons is also, quietly, an observation about information. Physicists sometimes describe C as the maximum speed of information transmission. No signal, no message, no influence can travel faster than C. This is not a statement about the engineering of transmitters and receivers. It is a statement about causality. If information could travel faster than C, it could, in principle, travel backward in time in some reference frames. A message sent faster than light could be received before it was sent in a frame moving at sufficient velocity relative to the sender and receiver. A universe where messages could arrive before they were sent would be a universe where the concept of cause and effect loses meaning. Physics would be internally inconsistent. The equations of mechanics would produce contradictions. A universe with faster-than-light information transmission would not be the universe described by special relativity. It would be a different kind of universe governed by different laws, if it could be governed by consistent laws at all. The speed of light is therefore the speed of causality. It is the maximum rate at which the present can influence the future. It is the boundary within which the universe maintains its logical consistency. Every physical law, every interaction, every force, every field operates within this boundary. The particles that compose you interact with each other through forces that propagate at most, at c. Your neurons transmit signals at a tiny fraction of c. The light that enters your eyes travels at exactly k until it is absorbed. You are a causal being, fully embedded in a causal universe. The speed limit is not your ceiling. It is your home. Come back to the room. Come back to the chair, the stillness, the familiar walls. Come back to the body that has been moving at millions of kilometers per hour. This entire time it has felt nothing. Right now, as you sit, the GPS satellites passing overhead are receiving relativistic corrections. The muons born in the upper atmosphere are surviving longer than classical physics predicts, because time slows at their speed. Every particle accelerator on Earth is observing massive particles approach cis asymptotically, spending more and more energy for smaller and smaller gains, exactly as the equations describe. The universe described in this video is the one you are sitting inside, not a theoretical future universe, not a simplified model that works approximately at some scales. The one where GPS requires relativistic corrections to function. The one where muons reach the ground because time dilates at high speed. The one where every proton in the LHC confirms millions of times per second that the energy required to push a massive object towards C grows without bound as C is approached. You cannot travel at the speed of light, not because the engine does not exist, because you have mass. Because mass creates the resistance that the Lorentz factor describes, because the Lorentz factor approaches infinity as C approaches, and therefore the energy required approaches infinity before C is ever reached. You also cannot travel at the speed of light because you are made of something different from light. A photon has no rest mass. It does not experience time. It has no duration, no aging, no history. It is not alive in any sense the word applies. It moves at c, because c is the only speed at which a massless field disturbance can propagate through the vacuum. It cannot move slower. It cannot stop. You can move slower. You can stop. You have mass. You have a rest frame. You have duration. You experience time. All of those things, the mass, the rest frame, the duration, the experience, are the same property described from different angles. They are what you are, and what you are is a thing that cannot reach C. This is not a constraint placed on you. It is a description of you. The speed limit is built into the same structure that makes you real. The same equations that forbid you from reaching C also describe the atoms that compose you, the forces that hold those atoms together, the energy that lets them form chemical bonds complex enough to produce a nervous system capable of asking this question. The universe has a speed. It is the speed at which the universe communicates with itself. You are made of the universe, operating within the universe under the same rules that define what communication means. You cannot outrun the speed of causality for the same reason you cannot exist outside of space-time. You are inside it, completely, all the way through. You already knew this, in the way that the body knows things the mind has not yet articulated. You have always felt that stillness is possible, that rest is a real state of being, that time passes at a reliable rate, that there is a here and a now and a consistent world around you. All of that feeling comes from the same source. You have mass. You have mass. You have duration. You live inside time rather than outside it. A photon does not have that luxury, or that burden, or that gift. It depends on how you read it. The room is still here, the floor is still under you, and outside, the universe is moving in every direction at once, at every speed below a single absolute limit, carrying everything that has ever existed toward whatever comes next. At exactly one speed, one very specific speed, there is only light, and light does not know it is moving. Good night. The question posed in the title has been answered now in every direction. Physics allows. You cannot travel at the speed of light because you have mass. Mass interacts with the structure of space-time in a way that makes C an asymptotic limit. The energy required to reach C is infinite. The mass of any object at C would be infinite. Time for any traveler at C would stop. The object at C would not experience anything. You could approach C asymptotically. You could travel at 99% or 99.9% and use the resulting time dilation to cover interstellar distances within a human lifespan. But the cost is permanent temporal separation from everything you left behind. The universe will not hold still. Everyone who watched you leave will age and change and die and be replaced by people who have no memory of your departure. The workarounds, the Alcubierre drive, the traversable wormhole, the quantum shortcut, all require conditions that current physics does not permit in any practical form. They are not solutions waiting for better engineering. They are proposals that require new physics, new matter, new properties of space-time that have not been observed and may not exist. And the speed of light itself is not a rule imposed from outside. It is the speed at which the universe processes cause and effect. To exceed it would not be to go very fast. It would be to violate the causal structure of space-time itself, to arrive before you departed, to receive effects before causes, to exist in a universe without consistent physical law. The answer to the title question is therefore both simple and vast. What would actually happen if you traveled at light speed is that you would need to first stop being the kind of thing that has mass. You would need to become light, and light does not travel anywhere. It is emitted at one point in space-time and absorbed at another, and between those 2 points, nothing happens. No duration passes, no experience occurs. The trip does not take place because the traveler has no time in which to experience it. You cannot be light and be alive. The speed limit is the boundary between those two categories of existence.